In this video, we're going to learn how to understand the output of the explain analyze statement. This video is a continuation of the part 1 I did for this video where we actually look at the output of the explain statement and is going to be building off of that knowledge there. So if you don't know how to understand the output of an explain statement, make sure to check out that video first. But let's get back to it. Our explain analyze statement is extremely useful because not only does it tell us the query plan, but it actually also executes the query for us and it gives us the actual results back. That gives us extra information about each node. Now, because the explain analyze statement actually executes the query, you're going to want to make sure that you actually wrap this between a begin and a rollback statement just to make sure that nothing actually is affected by executing the statement inside your database. Now, obviously, with a select statement, this is going to be less of an issue, but especially if you think about insert or update statements or delete statements, then these can actually cause problems because you may be adding new rows and you want to make sure that if you just care about understanding the performance, you don't actually make any changes to the underlying data that you have in your database, especially if those changes are accidental. So let's go ahead and execute one of these explain analyze statements. And if we look at the query plan output here, we can see if we compare it to what we previously had from just the explain statement that we have some extra information here. Most notably, the information that we can see at the very bottom is just summary statistics telling us how long it actually took to come up with a query plan, as well as how long the actual execution process took. But if we actually look at the individual node components too, we can see there also we have some extra informational statistics. In addition to just the cost and row and width estimates that we've had previously, we now also have the actual time components as well as the actual number of rows returned, as well as this loops parameter. The rows, just kind of as you expect, tells us the actual number of rows returned by this node, and the cost tells us the actual startup time and the actual execution time from beginning to returning the last row here. Now, both the row and the actual time are averaged per loop. Now, in our case, all of our loops are 1, but in some cases, you can see when you're doing your own query plans that this loop value is actually not 1, but is repeated multiple times. And in those cases, just remember that both the rows and the actual time are averages per loop, where the loop tells us how often this node was executed. Now, another interesting bit of information that we also get here is when we look at the filter clause, we can actually see how many rows were removed by this filter. Now, this can be another insightful piece of data to look at, because if you notice that this number is extremely large, that can actually indicate to you that you're reading in a lot of data that ends up being unused. And here you can also think about, okay, how can I either rewrite my query or maybe add an index or something like that, or change my approach to make sure that I'm not unnecessarily reading in and filtering out a lot of data that I don't need. Because if we remember previously, the biggest factor for us is just going to be how much data do we actually need to go through. And if we can reduce the amount of data that we're reading and that we're sifting through, our queries are going to run faster. Now, what's important to know about our query plan is that our query planner actually uses the Postgres table statistics to understand and formulate its plan. Now, the Postgres statistics give statistical information about each table, such as distributions of values and the like for each column, and it uses that information to decide on what the best plan of action may be. Now, generally, this does a pretty good job. However, sometimes this information can actually be outdated. Now, you can usually encounter this sort of circumstance if your table is undergoing heavy change. For example, you have a bunch of upserts, inserts, and delete statements, and your table is constantly changing very quickly. In that case, your auto vacuum may not actually have had enough time to trigger a table statistic update, and your table statistics may be out of date. Again, generally, this isn't that big of a problem because these are general statistics about your table that are not going to change very much. However, if your table is changing frequently and dramatically, then this can actually have pretty severe query implications. Now, we can update our table statistics manually by just doing this analyze statement here on our table, which is going to update it for us. However, how do you know actually if your table statistics are out of date? Well, a good thing to look at here is comparing the estimated number of rows returned versus the actual number of rows returned. And one important thing that you're really going to want to look for here is not if they're a perfect match, But generally you want to look for, is one of them 1 and is the other one not 1? And especially if this difference is dramatically large, then that can actually have a pretty significant impact on our query, because the way that our query planner deals and approaches with either having 1 or a non-1 number of rows returned is actually different. Because if it estimates that only 1 row is returned, it may think it can take a different strategy that for 1 row would be pretty efficient, but would not be efficient if you had like 10,000 rows. So just be aware of if there are any of these differences where one component is 1 and the other one is not 1. In our case, we have small differences where we have like a 1 and a 6, but these differences are really negligible, and so we don't really need to worry about them too much. However, if you do ever see something like this, then this should be kind of a warning flag for you. Now, generally, the way that you want to approach this is not just running an analyze statement before you execute every single query, but maybe what you want to do is just take a step back and think about, how is your database actually being used by your application? Why are all of these changes happening so frequently? And are there maybe series where you can instead have like bulk changes so that all this stuff is not constantly happening? And really at this point, you want to take in the bigger scope of the problem that you're trying to solve and maybe take a look back and ask, am I approaching this problem correctly, or is my application maybe misusing the database and actually, as our load scales, causing problems for our database and just keeping all that information up to date? Finally, another extremely cool keyword that we can add to our explain analyze statement is buffers. Buffers tells us about the temporary memory that's being used to execute these queries. And if we see a high number of buffers being used, that means a lot of data is going through, and depending on how much data is actually being returned, this may or may not actually be necessary. Each buffer represents 8 kilobytes of memory, and we can see in our query plans here, we have 1 buffer used for loading the event table, which makes sense, it's a really small one. And then we can see here by going through our user event log table, we have 40 buffers required here. Next to the buffer, we see this shared hit keyword, which means that our results are actually already stored in cache. And this is because I've already executed this query before. So if you want to get rid of this and see what it would look like fresh, restart your Postgres, and if you rerun it now, we can actually see that we also have this read component. And this means that we're actually reading this data from disk. Obviously, optimizing around having cache data is not really a reliable strategy, because you could just have a similar query being run just moments before by a different user using your application, which has happened to cause your data to be cached. So generally what you want to do with buffers is just be aware of how many buffers you're actually using. How much buffer space do you need to reserve and be able to have available to sift data in and out, and how much of that are you actually using? If you're using a high number of buffers, especially if this is combined with seeing high number of rows excluded in the filter by clause, that really means that you're sifting through a large amount of data that's then being discarded, which again indicates to you an area that maybe this is something that I can optimize. Either I can already directly reduce the amount of data that's coming in by adding maybe pagination through a limit and offset statement, or maybe adding a proper filter by using a where clause there, or maybe doing an inner join to reduce the amount of data that is actually going to be outputted. Or maybe you just think about your query and see if there's a different way that you can rewrite it or reformulate the problem. But anyway, having a high number of buffers, again, means having to sift through a lot of data, and this is something that we want to reduce. And the more that we can reduce the amount of data that we actually have to deal with, the faster our queries are going to run. So buffers can be extremely useful here because it really also points out to us these data-heavy components in our queries so that we can actually follow where is a lot of this data being used. So to summarize, explain analyze is extremely useful because not only does it give us the actual query plan, but it actually also executes the query for us and gives us actual runtime statistics about everything. We can further supplement the data that we have by adding this buffer keywords to also get information about memory buffer usage so that we can see even more clearly where we're actually sifting through large amounts of data, even if that may actually not be part of the final result. We can think about optimizing these parts of the query. However, keep in mind that not every query can be optimized. For example, if you're doing a select star from your table without any filters or anything, there's not much that you can do about it. At the end of the day, you're going to have to read all that data. But something important to always keep in mind is the context of your problem. Take a step back and ask yourself, what problem am I trying to solve? And is this really the best way to solve it? Do I really need to read all of that data from my table? Can I really not apply a filter or pagination or some sort of other method to reduce the amount of data that I have? Especially if you have larger and more nested queries, you may think about either pushing filters up to actually reduce the amount of data that you're taking in, or also pushing up pagination components so that you're not doing a limit at the very end, but rather doing a limit at the very beginning. I actually have a completely whole separate video about optimizing your query performances that goes into much more detail about this, which you can check out here. But just keep in mind that Explain and Explain Analyze is a tool that can help us understand our query performance. But at the end of the day, we as the developers are the ones that are going to have to assess these results in the context of our problem and think about, okay, can we use these results and maybe optimize our query somehow based on what we're seeing in this Explain and Explain Analyze statement, or actually can we reframe our problem, or are we not approaching our problem in the most optimal way that is actually leading to a maybe sub-ideal query plan where we're sifting through a lot of data that we actually don't end up needing in the end.